So today we began our lesson looking at a demonstration given by Professor Lewin, and I recommend it if you want to look up Lecture 31, Physics 1 in MIT Lewin on YouTube. You should be able to find it, and if you go to 817 and watch for a couple minutes, you'll see this. There's a spring and there's a mass on an air cart, and he pushes it, and it's going back and forth at about 1 hertz. And so then he's got a mechanism that is there that pushes the system at whatever frequency that he wants. And so, he starts pushing it at a slow pace, back and forth, and it's not moving a whole lot. And then he starts pushing it back and forth at a faster pace, and it turns out it's still not moving very much. But when he pushes it at its natural frequency, which was about 1 hertz, about 1 cycle a second, it starts to move back and forth, and the amplitudes get really big. And so this was introducing the idea of natural frequency. Natural frequency has to do with the characteristics of a particular object. Every object has a natural frequency. So if you push something, you vibrate something, it's going to go back and forth at its natural frequency. And pendulum is a great example. If you take, you could even take anything that's on a string or whatever, and if you hit it, it's going to be going back and forth at a certain rate. Now, if you have a short pendulum, the short pendulum is going to go back and forth, pretty rapidly. A long pendulum takes a longer amount of time to go back and forth. And so what determines its natural frequency is how long the string is. And so, if you have a setup like this, and this is a great example here where you have, 4 pendulums, and they're all tied together with this rubber band, and you start to move one of these back and forth. Now this is going to be moving back and forth, which is going to be moving this back and forth. Now it's going to be pushing each of these back and forth, but the only one that's really going to react is the one that it has the same natural frequency, has the same length, because as this gets forced back and forth, this one down here is not going to go very much. This one here is not going to go very much because the natural frequency isn't the same. But this one's going to start to move back and forth with this one, and both of them are going to start to move back and forth because they have the same natural frequency. And this, rubber band is going to be moving back and forth at its natural frequency, and it's going to be, greater and greater amplitudes. And so what resonance is where you're pushing something, you're forcing something at its natural frequency, and the amplitudes get very big. And so, in this case here with this picture, the natural frequency of this one and this one are the same. So if this one's moving back and forth, let's say you push it and it's moving back and forth, it's going to be pushing this rubber band, which is going to make this one start to go back and forth at a large amplitude. The other ones are not going to do a whole lot because, it has a different natural frequency. This is like if you're pushing someone in a swing. And if they're in a swing, there's a very particular time at which you want to push them. And that's right when they're at the highest point here, and then you push. And they're here, and then you push. And it turns out you're pushing at the same frequency as the person is actually going back and forth. And again, you get the large amplitudes there with that. So there was a bridge, it was a suspension bridge that if you fast forward that clip to 4026, I again recommend that. You go to 4026 and you can watch it. There's a bridge that was built that was actually set up as a suspension bridge. Cars could go across it, but it was suspended, and so it was kind of free to move. Now, it turned out that wind would come across it and cause the bridge to start to actually go back and forth. Now, one day, the wind was so strong that it actually started to resonate. It started to be pushed at its natural frequency, and the whole thing, broke apart, and the bridge was demolished. And so, very real, striking example of that with the Tacoma Narrows Bridge. Another thing that we talked about today is with aircraft. If you have an aircraft that is getting tested for flight, and I've got a friend that works for Cessna out in Wichita. What happens is, as the air comes across an aircraft at a particular angle particular speed, the aircraft itself, the wings have natural frequencies, the body itself has a natural frequency, the tail. And what the job is for those engineers is to actually determine what those natural frequencies are and make sure that during normal flight, the aircraft never gets in a condition where, you know, there's a forcing at its natural frequency. And so there's a video that I show in class that shows that. Now, what's kind of neat about this too, we talked about the ear and how it works today. There are small hairs located inside the fibers, or there's little fibers inside here where the liquid is being pushed. So essentially the tympanic membrane or the eardrum vibrates back and forth, then it gets this hammer moved back and forth, then through here it pushes the fluid back and forth, and there are fibers inside here that have a particular frequency that has its natural frequency. So for instance, there's hairs inside here that correspond to 512 hertz, and I hit the 512 hertz tuning fork, which shook the eardrum back and forth 512 times, which moves the hammer 512 times, which moves the fluid back and forth 512 times. And there's certain hairs that have that 512 natural frequency that when they get excited, they send nerve impulses through here and then to the brain, and then your brain says, 512. And so, you know, that has a natural frequency. And so the fact that, you know, you've got that tuning fork there that's exciting all of that, and resonating those small hairs in there that eventually send the impulses to the brain. It's just really neat how the ear works. So we did our string inquiry lab today, so you're going to need to make sure to make that up. Now, when you pluck a string on a guitar, it's kind of interesting. You know, you have all the strings in the guitar. If you have a tuning fork that matches the natural frequency of one of the strings, the tuning fork is going to be vibrating back and forth, which is vibrating the air. And then the air is going to come across these strings. Now, if the strings don't have the same natural frequency, they're not going to really vibrate very much. But if one of these strings has the same natural frequency as the tuning fork, it's going to start to vibrate back and forth pretty rapidly. The amplitudes are going to get big. And so yeah, we see that all over the place. I gave another example with like my car. This just started a few weeks ago, where at a certain speed, there's a rattle in my car, in the back of my car, and I can't, you know, figure it out what it is. And so at a very particular speed, when my car is going, it's shaking at a certain frequency, which then shakes whatever it is in the back of my car, and it resonates it, and it's pushing it at its natural frequency, and the amplitudes get huge, and it makes a noise, and it's pretty annoying.